Thank you for inviting me to be here today. I will admit I am not a public health person, so be kind. I'm an engineer, physical scientist, and I study air pollution. So I'm going to talk about how some of what I do can intersect with public health and thinking about air pollution from the measurements that we do. So this came out last month, actually less than a month ago, looking at 652 cities and linking ambient air pollution in terms of particulate matter to premature death. World Health Organization estimates that about 9 million people per year die prematurely from exposure to air pollution. Basically, particulate matter is the key issue there. Half of that being from outdoor air pollution and half of that being indoor air pollution in low or medium income countries where people use solid fuels to cook and heat. My research is focused on the chemical composition of particulate matter, and while particulate matter mass is great, and that's what we base a lot of our studies on, what I'm going to try to convince you of today is there's a lot of information in the chemical composition of particulate matter in terms of its sources, how it gets into the particulate matter, and its toxicity. I mean, we know asbestos is a key thing that we think about. Tobacco smoke is another thing. The chemical composition of those particulate matter is what is going to impact us in different ways. And so our work is focused on using what's known as an aerosol mass spectrometer. Unfortunately, this is not a cheap tool, so it can't be deployed everywhere. But it gives us a real-time measurement of the particulate composition. It can be size resolved. We can do single particle measurements. And essentially what it does is it just vaporizes particles inside of an instrument, and then we look at the resulting ions generated from electron ionization in our mass spectrometer. And we get about 2 gigabytes of data per second, which we then reduce significantly because you can't actually analyze all that data. And the core data that we get is a mass spectrum. And this provides information on the composition of the particles, as well as fingerprints for key sources. So we also get, as I mentioned before, size-resolved composition. And this is important from an exposure perspective. We know that smaller particles can penetrate more deeply into the lungs and have potentially more impact to health than larger particles, which may be deposited higher up in the airways. We can integrate those mass spectra into concentrations of different species, so things like nitrate in blue, sulfate in red, organics in green, ammonium in this orangish color. These give us information on the concentrations that we're measuring at any point in time. And this is an in situ measurement, so we're measuring at a particular point. We often do this at fixed sites. So in Philadelphia, for example, we made measurements in the wintertime. And if you take the about month of measurements that we did and you average all of it together and you say how much is nitrate, how much is sulfate, how much is ammonium, you get a pie chart that looks something like this. And one thing I want to stress is that the majority is what we call secondary. So this isn't directly emitted. This is particulate matter that is actually formed from chemistry that happens in the atmosphere, and then that chemistry generates species that don't want to be in the gas phase and they want to be in the particle phase. And so they condense onto the pre-existing particulate matter and grow that mass. Primary makes up about 20%, and that's things like black carbon, traffic-related pollution, cooking, wood burning, and I just mentioned these. So the primary is what's directly emitted as particles. It's that bus in front of you, that puff of black smoke that you see coming out of the bus. That's a primary emission. Cooking, if you're frying something, you can feel the oil on your face. That's basically particulate matter depositing on your face. Wood burning is pretty obvious. We know that smoke comes from fire, and that's another, in the wintertime in Philadelphia, a luxury that we don't really necessarily need to do, and it makes up about 4% of the particulate matter. But all of these potentially have different chemicals have different potential effects in the body, and that's something I want to think more about. In addition to what's primary emitted and what's generated in the atmosphere through chemistry, we can also start to tag these chemical species to their sources. So this nitrate comes from NO and NO2 emissions, is what we call NOx. These get oxidized in the atmosphere. These typically come from tailpipes or industrial processes, which are at high temperature. SO2 is decreasing, which is nice because we're burning less coal. And that SO2 gets oxidized to sulfuric acid, combines with ammonia from Lancaster. If you're familiar with the area, this is the farming area, and you get ammonium sulfate. And so that makes up a pretty significant fraction in the wintertime in Philadelphia, although that's going down because sulfate is decreasing. And then VOCs, volatile organic compounds from a variety of activities, can be oxidized to form the secondary organic aerosol, which is a much larger fraction in the summertime when we have more biogenic emissions from trees and other things. And so the seasonal differences are important, as well as the different sources in both human emissions and biogenic emissions from plants and things. So the relative fractions of all of these species are going to vary in place, in time of day, season. And so we try to do these types of measurements as frequently as we can, and typically over about a month period, to try to understand seasonal differences and other things. And one other nice thing that we can do is we can plop this roughly $500,000 instrument in the back of a van and drive around and make measurements and get about 2-second data. And so during my postdoc, I was in Switzerland, and we made measurements in a few different cities in Europe. And more recently, as a faculty member here, we've been doing work in Nepal, where we, after I got tenure, and so if my instrument fell apart, I still wouldn't get fired, drove this instrument around in the Kathmandu Valley. And I'll be showing some examples from cities in Western Europe versus Nepal, and thinking about the primary, secondary emissions and what's important depending on what city or region you're in. So I'll start with Zurich. These are measurements made by Claudia Moore, who's now a professor at Stockholm University. And driving around Zurich city center, you can see all these pie charts for different regions in the city. We did this drive about 20 times. And we can start to look at what the different chemical composition is in different parts of the city and learn from that. And so if you normalize to this background site here, this was off-road, it was kind of city center, and we used that as the base case to compare all these different neighborhoods that we're measuring to. You can start to see what pops up, what are the main drivers above this regional background that we're seeing in Zurich. So this regional background is what it looks like, and what you see is a lot of this black and gray color. That black and gray color is black carbon, and what we call HOA, or hydrocarbon-like organic aerosol, which is nerd speak for lubricating oil from diesel vehicles. So essentially what you're seeing is all of this variability is mostly driven by traffic emissions, by diesel emissions. Switzerland's a very affluent country. They've controlled all of their primary sources from industry and other things. And so what we're really left with in that situation is vehicles. And then here, and a couple other places here, that's wood burning. There's a couple neighborhoods in Zurich that still predominantly heat buildings with biomass. And so you can actually pick out those signals chemically in our data sets and see that this neighborhood, in addition to having higher traffic emissions in the background site, also has higher emissions from wood smoke. So just to kind of push that point home, the spatial variation that we're seeing in Zurich, a fairly affluent city, or very affluent city actually, is mostly from traffic, and Europe in general has a lot more diesel vehicles than the US. And thanks to the VW scandal, I think that's even going down in the US. Wood burning is still used even in developed countries and in many places, and can also contribute in certain areas to what people are going to be breathing on that kind of hyper-local scale. I know there's another speaker from Barcelona, so I thought I'd throw this up. This is another place where we've made regional measurements, and this was, again, Claudia Moore's second paper, looking at different zones. And so we're going now not just from the urban region, but also to the regional scale. So within the city center, this is kind of the city center, port area, more industrial zones, and then out into like the mountain ranges outside of Barcelona. And you can see, again, unfortunately we don't have the exact same graphics. The main changes, again, are these black carbon and some of this HOA. So this lubricating oil and black carbon. So again, in Barcelona, another city in Western Europe, that's fairly well developed with good regulations. The major drivers spatially for changes in particulate matter composition are from traffic. Dilution also plays a role. As you get farther away from the city, you mix in cleaner air and you drop down the concentrations in this pre-coastal mountain ranges. I'm going to contrast what we've been seeing spatially in Western Europe with this project, the Namaste project. Yes, we have a lot of fun with acronyms. And this has been a very good collaboration with our in-country partners at ECMOD, folks from the University of Iowa and the University of Montana, looking in South Asia where we don't have a lot of data. Funding agencies with a lot of money are typically located in the US and Western Europe, and so a lot of our research has focused on where the funding agencies and therefore the dollars are. So we don't have a lot of information on South Asia. We know that South Asia has a huge amount of emissions, and so we want to understand more about what they look like. industry is very different in South Asia. So one of the things we really wanted to focus on was both emission sources and then those ambient concentrations that we see in the chemical signatures from those. So this is a lot of information. I don't want to dwell on it, but essentially we went around in the Kathmandu Valley and we looked at regional specific sources. So brick kilns, agricultural burning, depending on what people are burning in fields, cook stoves in homes, as well as motorcycles, some irrigation pumps and other things. And the colors you see are reflective of the different compositions that are being emitted directly from these different sources. So one of the key things I want to draw your attention to, because it's going to come important later, is this red, this sulfate, is coming from the brick kilns. They use coal co-fired with biomass to make bricks in the Kathmandu area. And so that's going to help us identify that source rather easily. We made measurements in 4 locations within the Kathmandu Valley for about 2 weeks at each time to try to understand spatial variation from a fixed site perspective. So we're doing 24 hours of measurements, taking data every 1 minute, and then integrating that over the course of that 2 weeks. And what we can see really kind of makes sense. The Bode site we measured in 2015. Unfortunately, that got cut short due to the earthquake. That showed the highest concentrations overall and a significant concentration of sulfate compared to the other sites. And this is because it's actually adjacent to the brick kiln region. The Ratna Park region has the highest black carbon. This is city center, right next to a big transportation zone where a lot of buses and trucks go through. And so the highest black carbon is consistent with its location. And so you can see these chemical differences at these fixed sites if we compare. The Dhulakil site is on the edge of the valley, far removed from the urban center of Kathmandu, and it has roughly half the concentration of what we see in Kathmandu itself. And so you can see this regional to urban bump in overall air pollution due to the higher population and more activity going on in that region. The other important thing to note is that the biomass burning signature, the cook stove signature, was much higher in the Dhulakil region because it was farther removed from the urban area. More people relied on solid fuel burning to cook with. I also want to highlight the spatial differences. Oops, I went too fast. So sulfate, again, is a marker for brick kilns. All of these purple dots are brick kilns. Wind speed, low, overnight, going in this direction. And if we're doing our drive in our vehicle, we can measure our sulfate concentration as we drive along this road, and all of a sudden we get to the brick kiln region, it pops up. It doubles, actually. So you can see the importance of those sources on the regional composition, and what that means is anyone downwind in Kathmandu itself is going to be seeing those emissions and breathing those, whereas people upwind aren't going to. And so even within a small 30-kilometer difference in space, you have pretty massive differences in composition. Chloride and organics are also interesting. This massive spike in chloride that you see here is due likely to trash burning or agricultural burning near the side of the road. And so this is also important when you think about the more rural areas over here and the way that people dispose of things. It's going to change their exposure to different chemicals and what that might mean. And then finishing it off with the other things that we can measure, ammonium and nitrate also vary spatially. But the key here is that we're seeing 100 microgram per meter cube difference in concentration over a 30-kilometer space. A lot of that due now not to traffic, but to industries that are not well regulated because there is no regulation in place for brick kilns. There's a lot more open fires because there's no municipal trash pickup, and so you burn trash to get rid of it, things like that. And so the context of where the emissions are coming from change depending on the regulations that you have. So really just to summarize, the spatial variation is that primary sources are really important, and as you start to improve your regulations and reduce industrial emissions, you get down to traffic-related things. In places with less or minimal regulation, we're talking about trash burning and industrial emissions and all those other things. And so that's driving a lot of the spatial differences that we see in our measurements. I only have a minute left, so I really want to introduce one last thing, and I'm not going to have a lot of time to go beyond that. But anyone out there, raise your hand if you spend more than 2.5 hours outside a day, on average. Yeah, that's pretty much typical when I ask this question. Americans and many in Western Europe spend more than 90% of their time indoors. And so the point I want to make here before I get cut off is that we spend our 90% of our time indoors means that our exposure to outdoor pollution happens indoors. And so we've also been investigating what happens to outdoor air pollution when it comes indoors. We heat in the winter, we cool in the summer, that can change the composition. And we've been investigating this in more recently in my work in trying to understand how our exposure indoors is related to the outdoor air pollution, because it basically happens that way. So I'll skip over all of this stuff. I knew I wasn't going to get to it. But conclusions and parting thoughts. Indoor spaces are where we are exposed to outdoor pollution here, not necessarily everywhere. And really where we want to start to take this is what are the health endpoints of all these different chemical species that we're measuring. Now that we're starting to get a handle on the secondary versus primary and the different sources and what they mean, how can we take that knowledge and really expand it to larger data sets to go beyond just the total PM mass in terms of health? Thank you.